Our second speaker this afternoon is Susan Shah from Velasys Digital. Please welcome the speaker.
Is there a clicker for
Come on up. Looks like this is going to be a clicker.
Okay.
And probably a laser pointer.
I don't think the laser works.
No, it doesn't work.
Yeah.
And let's see how to play this.
Just click view.
You,
Probably full screen mode.
do you know how to start this?
I can just full screen.
You're on. Okay.
Okay. Sorry, I'm waiting. Oh, I think the mic works. Okay, awesome. So first of all, I want to thank CMC for organizing such an awesome event. And thank you for inviting me to speak. So my name is Susan Shah, and I'm a data scientist at Velasys. So Velasys has traditionally been a print company. We make a bunch of things. Among many, we make the shared mail packets that you receive in your weekly mail. And recently, it acquired a digital component that works on digital advertising. So that's where I'm working at. So today, I want to talk about how to use Ensemble Learning for predictive modeling purposes. In particular, how to use stacking, which is the Ensemble Learning method, for making predictive models. And I don't think the clicker works, so I guess I'm just going to stick with the laptop. OK. So the problem we're going to try to predict for this talk is going to be the event of a user making a purchase on the internet. So that's a crucial problem in digital advertisement. So first, I'm going to tell you guys what the business problem is we're trying to solve, so you would be able to understand the context. And then I'm going to dive into introducing Ensemble Learning and in particular stacking. Then I'm also going to give some details in how we might want to optimize or tune a stacked model. And finally, I'm going to touch on how we implement and deploy stacked models in our system. So what is the business problem in this case? So I don't think many people here know how digital advertisement works. But when you're browsing the website, you probably usually see like a lot of ads on the web page you're browsing. For example, you can see at the top of the page, there is like a banner ad. This is CNN.com. At the top of the page, you can see a banner ad that's for Toy Story 4 related merch on Wayfair.com. And here at the bottom, you can see ads for Bose headphones. So I'm one of the people you could blame for seeing ads on the internet. So how does the process work? So it all starts with when a user has a general browsing session of a website. In this case, it's CNN.com. And let's say if the website is ad enabled, then that signal is going to go to what's called an ad exchange, which could basically be thought of as a platform between us and users browsing the website. And then the ad exchange is going to pass us a request. And we receive about 120 billion requests on a daily basis. And then we're going to look at the user and look at which website they're browsing at. And we want to decide whether we want to serve this user an ad or not. And if we decide yes, then we're going to come up with an amount that we want to pay for this opportunity. And we're going to participate in what's called a real-time bidding process, which is basically just an auction. And if we win the auction, then we are going to serve the user an ad. So for 99.9% of all the requests we get, we respond within less than 10 milliseconds. And at this time, we're going to drop a cookie on this user if we don't already have a cookie. And with that cookie, we can track the user's internet browsing activities. For example, how long they've been active and what type of web pages they're browsing. So in our system, there are about 1 billion users for which we have such data for. And at a later date, if this user makes a purchase on one of our client's website, let's say they bought some merch related to Toy Story 4 on the Wayfair.com, then that purchase signal gets sent back to us using what's called a pixel we placed on our client's website. And we would get credit for serving the user ad, and later the user made a purchase. So just to summarize, so as a digital advertising company, we run campaigns for our clients, which are usually brands or ad agencies. And the client usually has a certain set of key performance indicators they're trying to drive. For example, they want to increase the purchase rate of their product. And we, as an advertisement partner, would receive credits if we serve an ad to the user, and the user later makes a purchase of our client's product. So we want to serve ads to people who are more likely to make a purchase, or more generally speaking, perform a conversion. So in the case of an automotive campaign, it could just be signing up for a test drive. So in order to achieve this, we need to predict the likelihood of users converting given the data we have about them. So you can imagine we have all these different types of data about an internet user, like what websites they're looking at, how long they've been active, what were their previous interaction with ads, what are their interests, and what are their demographics. So using all those information, can we predict whether the user will make a purchase in the future? And there are some additional requirements that I want this process or solution to satisfy. So first, I want it to allow multiple contributors over time. So by that, I mean it should allow multiple data scientists and engineers to work on the solution at the same time. We don't just want one person to work on this project at a time, but we also need that each person's individual contribution doesn't basically wreck the whole system. The second requirement is we want the solution to be generalizable to other use cases. We don't want to build a piece of very expensive architecture that uses a lot of engineering resources, but only for a one-off case. So with that, the solution we chose is an ensemble learning approach. So what is ensemble learning? Well, it's really just the tool of combining the predictive power of multiple learners to obtain better predictions than using just one learner alone. So since we're using multiple models, since we're using multiple learners, it could combine multiple models to give a single prediction. And with that, it increases the diversity of the models or algorithms used. And it has been shown to improve the predictive power of the individual models. So what are some examples of ensemble learning? So the one that's, I guess, most commonly used is called bagging, which stands for bootstrap aggregation. So in the case of bagging, the individual base learners are trained in parallel. So it's usually used to reduce variance of the base learners. And each learner is often trained on the random subset of the training data and also on a random subset of the features. And when it comes to time to make the prediction, each base learner is going to vote on the outcome using some weights. And the weights is probably going to be dependent on the accuracy of this individual base learner. So let's just, in the case of a decision tree, we're going to train a bunch of decision trees in parallel, each on a subset of data and on a subset of features. And when it comes to time to make the prediction, all the individual decision trees get to vote on the outcome. So with that, we just get a random forest. Another way of doing ensemble learning is called boosting. So instead of training the base learners in parallel, which is what happens in bagging, in boosting, all the base learners are trained sequentially. And it's often the case that samples that were misclassified by a previous learner would receive more weights when we're building the next learner. So again, let's take decision tree as an example. So we're going to train a decision tree on a subsample of data, and we're going to predict on the whole data set. And we look at where all the samples are misclassified. And we're training a new decision tree. During the training and evaluation process, the misclassified samples are going to receive more weight. So we're going to just keep iterating on this process until we're no longer seeing improvement in accuracy, or just reach a certain number of maximum iteration. So that's basically how boosting works. And there are different ways of boosting. One is adaptive boosting, which is basically just does what I described. So we build the base learner sequentially, and the samples that were misclassified receive more weights in the next iteration. And there is what's called gradient boosting. So where instead of having each individual base learner predict the final outcome or the labels, each model is actually fitted to predict the residual error of the previous model. And also, we also assign more weights to samples that were misclassified in the previous iteration. So this is very similar, or it can be thought of as just performing gradient descent on the error function, hence the name gradient boosting. And then there is XGBoost, which is basically a full-featured efficient implementation of gradient boosted trees. So it supports fast learning through distributed and randomized computing. In decision trees, the most expensive training step is probably just finding the best tree split. And XGBoost uses approximation algorithms to evaluate and find tree splits. And it also supports regularization and tree pruning. And it also has good native support for missing values. So you probably have seen it around a bunch. You can find it in almost every winning kernel in Kaggle competitions. It's been shown to be good at predicting rare events and distinguishing signal from noise. So, and they approach, those are some examples of ensemble learning. And the ensemble learning approach we took is stacking. So what is stacking? Well, as I said, it's another ensemble learning method where you can thought of it as basically a layered structure. So it's going to have different layers. In different layers, we have different models. So predictions from models in the previous layer is going to be used as inputs to models in the sequential layer. And those models in the sequential layer are going to train on those inputs. And after going through many layers, it's going to produce a final outcome. So it may be just clearer to just look at the picture. In this case, we only have 2 layers. The first layer has 4 base models. The second one has just 1 model. And the data would go into the first layer to the 4 base learners. And each of them is going to make a prediction. And all the predictions are going to feed into the model in the second layer. And that model is going to make a final prediction. So what are some benefits of stacking? Well, since we are allowed to use basically as many models as we want, stacking increases the diversity of the algorithms and models used naturally, and it can decrease bias. So rather than winner takes all, we could combine different data sets to decrease bias in this case. It also enables the parallel development criteria that I mentioned in the beginning. So each individual could work on a different base model. And when they feel comfortable with the base model, they could just add that base model to be stacked and without having to interfere with each other's work. And since we're using different models, we could also naturally capture different categories or features with different base models. So this may become more clear as I show you an example. And if we're just to combine those different categories of features in a single model, that can get computationally expensive very fast. So here is an example of how it might work in this case. So we could just have 2 layers of models. In the first layer, we have 3 base learners. In the second layer, which we have just 1 model. So we could have an XGBoost classifier that predicts conversion based on users' browsing history. We could have a random forest classifier that predicts conversion based on users' response to previous ads, like whether the user interacted with the ads at all, whether the user clicked on it, etc. And then we could have, I guess, a logistical regression in this case to predict conversion based on users' activity level. For example, what time of day is the user active and how active is the user in general. So each of them is going to produce a probability of conversion. And all those is going to go as inputs into another XGBoost classifier. And that's going to make the final prediction to predict the probability of conversion. So that's basically the theory behind the architecture of the solution we chose. So next up, I want to talk about how we might want to optimize and tune a stacked model. So in particular, we have this fairly standard machine learning pipeline where the train validate test pipeline, where we train the model first, tune the hyperparameters on some validation set, and test the model performance. So how does that apply in the case of a stacked model? So in stacker tuning, so each individual models should be tuned for hyperparameters. For example, we could use a randomized search in the hyperparameter space and together with the k-fold cross-validation to select the appropriate hyperparameters. One thing, so before I go into this, I should let's just assume right now we only have 2 layers of models. We have a bunch of base learners in the first layer, just one model in the second layer. And I'm just going to call that model in the second layer the stacker. So one thing that's particular to a stacked model is that when we're using k-fold cross-validation, I suggest we make the folds of the base learners and the stacker to be different. So for example, let's tune the base models first using some k-fold cross-validation. So we divide data into train and test folds and select some hyperparameters. So after we finish selecting hyperparameters for the base models, when it comes to tuning the stacker, each base model are going to fit on the train folds and predicts on the test folds. And those predictions on each test fold are now going to form new folds for the stacker. So, and then the stacker, so we're going to then recreate train and test folds for the stacker using these new folds. So we're basically performing this kind of stackation of data between the data for the base models and the stacker. The reason we want to do that is we don't want the stacker to improve the in-sample estimation accuracy of the base models. We really want the stacker to increase the out-of-sample prediction accuracy. Therefore, we want to do some form of shuffling of the tuning data. I'm not suggesting you should, because I'm not saying you have to do it the exact same way, but I highly suggest you do some shuffling of the data. And after the stacker is tuned, we refit the whole models on the entire data set. And when we're using stackers, there are some things we need to pay attention to. So due to its sequential nature, it likely leads, or it's prone to be overfitted. So we need to take some precautions against it. First, we need to make sure there is enough data to support stacking. So there's one case in which stacker has not been shown to have stronger performance than base models. It's the case when the base models have high variance. So we want to avoid that. And we also want to use some form of regularization. So for example, if your base learners are decision trees, you may want to put some cap on how deep the tree could be, how many samples we're considering at each split, or what's the minimum samples needs to be in each leaf node. We could also use early stopping, etc. Basically, some regularization. And another thing that's somewhat unique to the stacker is we want to use mutually orthogonal base models. So here's what I mean. So when we're combining the predictive power of different base models, it's desirable that those predicted probabilities or the output of the base learners have low correlation. So I guess intuitively, that could just be thought of as the base models, each of them are skillful, but in different ways. If they had high correlation, then we're just sending repeated information into the stacker. Not only that's a waste of resources, it could also lead to overfit. So we want to avoid that. And next up, let's talk about evaluation metrics. So what evaluation metrics should we use? Well, the answer is it really depends on the problem you're trying to solve. So let's just revisit the problem in this case. So for each ad campaign we have in the system, there is we associate a list of users, basically a ranked list of users that we want to serve the ads to. And we call this ranked list an audience of this ad campaign. So now we have this predictive model, let's say a stacked model, that produces the probability of a user converting in the future. So that already gives us a natural ranking of the users. And for each audience, we have 2 goals. So the first one is we want to put as many future converters as possible in the audience. Therefore, we could serve ads to people who are more likely to make a purchase. The second goal is we want to rank future converters higher than the non-converters so that those converters could be served first and also priced higher in this case. And based on the two goals, we came up with the two evaluation metrics. The first one is recall, just pertaining to the first goal. The second one is called NDCG, which stands for normalized discounted cumulative gain. So this is a popular metric in information theory that basically evaluates the quality of a ranked list of documents. So it evaluates the ability of a ranked list to put relevant items at the top and irrelevant ones at the bottom. By cumulative gain, I just mean we get points for putting each relevant item in the list. And for discounted, I mean we would get less points if the relevant items are put lower in the list. So basically, we're discounting by the position of relevant items. And if we just use discounted cumulative gain, you can imagine it's easier for a longer list to have more relevant items. So in order to facilitate a comparison of lists of a different length, we want some form of normalization. So we're just going to divide by the discounted cumulative gain of a perfect ranking. So that, and due to normalization, NDCG is going to have a range between 0 and 1. So here is the math behind it. What you really need is just defining a relevance value for each relevant item. So in this case, we're just going to give 1 to all the converters, and they're 0 to the non-converters. And here is an even example if you want to do the math yourself. So far, I've told you what the problem is, what our solution is, and what are some ways to optimize that solution. So now I want to spend a couple of minutes talk about how we implement and deploy stacked models in our system. So there are some things to consider when we think about building a model deployment pipeline. So first of all, needs to be scalable. So if you remember, as I mentioned, there are roughly 1 billion users in our system where we have a good amount of data for. So this pipeline needs to be able to fit hundreds of models daily. And for each model, it needs to be scored on that 1 billion user. So this pipeline needs to support that. It also needs to be user-friendly. And by user, in this case, I really just mean the data scientists who are developing the models. And we tend to write things in Python, so this pipeline should be able to support that. And finally, it should also be generalizable. Again, this process needs to be generalizable to other model fitting and deployment use cases, because such a pipeline takes a lot of engineering resources to build. We don't want to build an ad hoc solution for an ad hoc problem. So we looked around for different things that could achieve this. We didn't like any of them, so we just decided to basically build our own solution. So what we did is we wrote our own in-house library called Hunch that allows the functionality of Python and the speed of Scala. So what Hunch does is it supports serialization of scikit-learn models and XGBoost models into Hunch representations, and deserialization of Hunch representations into Scala functions. So here is how it works. So when we're fitting the model, it's going to be done in Python. It's usually on a smaller scale. We fit each model roughly on 200,000 users. And we're going to serialize the fitted model in Python into a JSON object that goes through Hunch. And then Hunch is going to deserialize it into basically a Scala UDF that's going to take a vector of numbers and spits out a class-like probability. So when it comes time to scoring, we're just going to evaluate that UDF on our 1 billion users for each model. And here are some performance statistics. So in our system, we run about 600 models daily to predict from our users. And each user is a row of 7,000 plus entries of feature vectors. And we make an estimated number of 200 billion row evaluations every day. And the models are running batch. But by the models, I mean the jobs that are actually scoring scoring the models on our 1 billion users. And that takes about 5.5 hours serially, and about 5,300 hours virtual core time in 5,300 hours virtual core time in Spark. I don't actually have data to tell you how long it's gonna take if we were to this in Python, but I don't think it's realistic for that to support these jobs to be run daily. So that's kind of concluded the implementation and deployment piece. So I think that's basically all I have to say. So in this talk, I told you about, I gave you a business context or a business problem we're trying to solve, and walk through the solution we chose and why we chose it. And finally, I touched on like how we want to implement and deploy things in production because it's a real world problem. So hopefully you were able to take something away from that, like maybe whether it's the stacking part or the deployment of real models into a real world production system. So hopefully you were able to take something away and apply it to your own problem. Thank you.
You mentioned that diversity of the model plays an important role when we build the stack ensemble models. And another way to increase that diversity is to use different subsamples, different training sets. So I was wondering if you thought about incorporating that, like for example, training different gradient boosting models with different feature sets when you are building your stack ensemble models. Also, I was wondering if you tried different stages, like multiple stages of stack ensemble, 3 stages or 2 stages. And if you did it help increasing the predictive performance?
Yeah, so for the second question, I want to answer that first. No, we did not try to train different stages of different models, just because even though with a lot of acceleration with the Hunter library, this job still takes quite a while. So we were first developing this, we were cautious about making the scoring process longer. But since then, we actually made a lot of progress in terms of speeding things up. So I think it's time for us to go back to maybe redo the process. So maybe training different stages is something we could consider. And for the first question, we are training different features right now for different base models. As I mentioned, we could use different categories of features, but we're not necessarily training them on different data. Maybe I guess by data you mean different samples, is that what you meant? So the reason is what we're trying to predict is a rare event. Like the user making a purchase on the internet, it's quietly rare. So what we often do is we oversample the converters in the data set and undersample the non-converters
It affects
the data set. So we almost always want to keep the converters in the data set. Maybe we could try to rotate the non-converters, but that's not something we did.
I have 2 questions. The first question is about, so I noticed you use different features for the base model. So how do you handle the missing data? And the second question is, you optimize the base models separately. Is that because and the best parameter for the base model may not the best parameter for the overall the final models? So is that a way to optimize all the base model together to get the best final models? I'm not sure if you understand.
So I think your second question is asking, I guess I kind of understand what you're asking for the second question. So the reason we do this is we want to basically have the best performing base model. So I'm not saying that that's what everyone should do, but what we think makes sense is to have the best performing base models. So each individual models is at their best capacity, and then we do hyperparameter selection for the stacker so that the stacker has the best capacity to pick the best performing base models. So in that way, we have the best performing models, a stacked model as a whole. So that's our philosophy of building this. Sorry, I forgot your first question.
First question is, because you use different features for different base model, how do you handle the missing value for some features?
I think we just, I don't remember the details, but I think there are always enough non-converters in this case to give us the ones that with the least missing value. So we could just pick those. And I think for the ones that did not give us, we probably just filled in some default values for the actual missing values.
Thank you.
Got a more practical question, and that is if someone, and it's probably more likely someone like someone in this room, flushes the cache, clears cookies, uses NoScript and other tools, are you still able to gather data on them?
I guess the answer is probably a partial yes, because so cookies is one type of users within our system. There are also different types of users in our system. For example, we could just collect data based on a user's IP addresses and what type of browser they're using. Where we think this user who always uses the Windows computer with this type of browsers, who is always active during this time with this IP address, is probably the same person. So that's another potential user type we could use. So I guess there wouldn't be as defining as a cookie, but there are definitely ways that people could try to approximate for a user. Thank you.